In the past couple videos, we've talked about solving linear equations of single variables, and today we'll be doing a lot more examples of solving these type of equations. Just a quick recap, real quickly. In the last video, we said, okay, well, we have sets, and these are this is where our solution goes into, and basically what happened was this represents the number line. The equations of a single variable mainly deal with these sets, because there's just a bunch of solutions, and we'll see some interesting cases with these upcoming examples. So let's take a look at our first example. 3x over 2 is equal to 5 minus 39 over 5. Sorry, x over 5 minus 39 over 5. So there's a couple of mistakes that I see a lot of students make when they do this. They try to go gung-ho, and they really make arithmetic errors here. They, at times, like a common example is forgetting about the numbers in the bottom and just worrying about the top. And in fact, in that case, we'll be off by a huge factor, and that's not good. Because if that were a mathematical model, that model's way off. So, how would I attack this? Well, there's two ways. This is technically a linear rational equation, in the sense that it's just dealing with a bunch of fractions. Of course, we haven't talked about that. That's an Algebra 2 topic, but there's an easy way of dealing with this, and it's clearing the fraction. We could combine these x over 5s. We could combine these and then cross multiply, and that's just nasty. It's a lot more involved. Let's just clear the fraction. And what do I mean by that? So basically what's going to happen is we're going to look at each of the denominator, each of the factors in the denominator. So we have 2, 5, and 5. So we're going to think of a number that's in common with these numbers. So what's in common with 2, 5, and 5, and it's small? The smallest factor is 10. So what are we going to do with that? Well, we're going to multiply both sides by 10. And so on this side, that'll just give us 10 times 3x over 2. So it'll be equal to 10 times the quantity of x over 5 minus 39 over 5. On this side, 10 cancels out, and it becomes 5. That's 5x. The 10 distributes on this side. Alright, so that's saying, okay, that's 10x, and that's 10 times 39. Well, 10 over 5, that's 2x, minus, and then same case over here. So that just leaves us 2. It comes out to be 78. Yeah, 78. So 2 times 39 is 78. We solve this now. We just now, what we're going to do is we're going to subtract 2 from both sides, isolate the variables. 3x is equal to minus 78, divided by 3 on both sides. X is now equal to minus. Alright, and that'll be 26 minus 26. And we could also say in set notation, just minus 26. So basically that whole idea of this problem was we wanted to clear the fraction, getting rid of the denominator, because we don't want to deal with that. That's just nasty. And basically what we did was we multiplied by a common denominator, a number that the denominators had in common. In this case, it was 10, and we distributed across both sides, and it made it into a linear equation instead of having a rational equation. And in fact, that's going to be a common strategy in Algebra 2 that you'll see. So let's do another example. Let's do b. 0.3 times the quantity of x minus 6 is equal to 0.37x plus 11. So this is another straightforward case, but now we're doing decimals, and a lot of people just get scared of it. Just treat your decimals or fractions as real numbers. Oops, sorry, I didn't mean to scroll down. Just treat them as regular numbers. So basically what's going to happen is we're going to distribute 0.3 to both sides, or to not both sides, but 2x and 6. So I guess it's 0.3x minus 1.1. Sorry, not 1.1. 0.3 times 6 is 1.8. And we're going to say it's going to be equal to, so I can write that better, 0.37 plus 1.1. Okay. Now what do we do? Just like before, we'll just move coefficients to both sides. Minus 0.37 x minus 0.37x. I'm sorry about that. That should have been a minus. Alright, and then we're going to add 1.8 to both sides. 0.37, so 0.3x minus 0.37x is 0.0, oops, 7x. The 1.8's cancel. This cancels and leaves us with minus 0.7x. So we're going to divide by 0.07. And this results in x is equal to minus 10. So in sets, that'll be minus 10 on our number line. So for this problem, our idea was to just treat the decimals, or even if we have fractions, just treat them like real numbers. Let's look at our next one. 2x plus 6 is equal to 2x minus, 2x plus 4. So, just like before, we're going to distribute our 2 on this side. And so that gives us 2x plus 6 is going to equal 2x plus 8. This is 6, sorry about that. Let's make that clearer. Alright, subtracting 2x from both sides. We're going to add 6 both sides. This cancels and this cancels, gives us 0. Oops, that should have been minus. And that cancels. So on this side, it gives us 0. We have nothing on this side, because the minus, so this canceled out, and that canceled out. But now we have 8 minus 6. And that is going to equal to 2. Now we get a really interesting result. The reason being is now we don't have any variables on either side of the equation. There's nothing to isolate. We isolated our variables and they canceled out. There's nothing on one side, and we were just left with a number. And so basically what happens is we end up with an equality statement for real numbers. And if this ends up being true, we get infinite solutions. So if it's true, infinite solutions. Which we call, which we write with that superscript r. And the reason, what that means is we're saying every number goes into that equation, and it's true. But in this case, it's not, because this is a false equation. And so what happens there? So if it's false, we get the empty set, no solution. And we get the empty set, no solutions in our set. This statement is true. 0 is not equal to 2. So, therefore, we get no solution. Let's do our last equation. 3x plus 5 plus 5x is equal to 4x minus 2x plus 5. So the first thing we do, just like before, is we combine like terms, getting a single variable of x on both sides. So on this side we have minus 3x and 5x in common. So that's 2x plus 5, because that just stays the same. And we have on this side 4x and 2x plus 5. The 5 will stay the same. That comes out to be 2x plus 5. Now, just like before, isolate our variables of x. But, what do you notice? Well, that's going to cancel, that's going to cancel. So on both sides we get 0, it's going to be equal to 0. And is this a true statement? Does 0 equal 0? And essentially, yes, it does. So what does that mean? Well, going back up to here, if we said, if it's true, there's infinite many solutions. And so we just write, we denote that with the superscript r, the superscript r. And what that means is all real numbers. So we could plug in any real number into this equation, and it'll give us a number that's going to be on this number line.